This next section on fusion is really important, especially for our unit on astrophysics. But fusion is just when we have two lighter nuclei combined to form a more massive nucleus with a very, very large release of energy. Now, this naturally occurs in stars. All right? This is where stars get their energy. They have such a tremendous amount of mass that the gravitational pressure is so large that it's able to pull in all these atoms and bring them up to such a high temperature and pressure that fusion occurs. All right? So we have a possible, or probable, I should say, mechanism for the sun's fusion. It's what we call the proton-proton chain. All right? And what we end up doing is going from 4 hydrogen protons, basically, into 1 helium, all right, plus a release of a lot of energy. All right? And this is the major energy source or fusion reaction that's happening in the sun right now. So if we take these 4 hydrogen nuclei and add up their masses, we end up with this number here. It's on the screen. And if we compare this to the mass of the helium nucleus, we see the mass of the helium nucleus is less than this. All right, so we know that some of that mass has been converted into energy. So if we look for the mass defect, what we find when we take the difference between both of these numbers, all right, is some amount in kilograms that's missing. And so really this just ends up becoming a long unit conversion problem. All right. So there we go, and the difference here is 4.8 times 10 to the negative 29 kilograms. We want to convert this into unified atomic mass units, and then eventually we're going to convert to MeV per c squared. So when we do this here, this is our conversion, really long, obnoxious number. All right, there we go. And then we can convert this again to MeV per c squared from unified atomic mass units, and there we go. So there are all of our conversions. So we will end up over here reading as 26.9 MeV per c squared. And then again, obviously, you know, plug this into E equals mc squared. And when we do that, those c squared terms are going to cancel out nicely for us. And we end up with this release of energy, which, comparing this to the mass of the substance, is quite a lot. Okay? Let's consider a fun little problem here. We have our sun, has a radius given there of about 700 million meters, and it emits energy at this rate. Okay? So the nuclear reactions take place in the core, right, which has a radius that's a quarter of that, the entire sun. So what we want to do, assuming this constant density here, determine the number of nuclear reactions occurring per cubic meter per second in the core of the sun. All right? Pardon me, we're not going to assume constant density. We don't even have to think about that. Sorry, it's not even a concern. But let's quickly figure out the core, the volume of the core. Okay? We do need that since we're basically figuring out a reaction density here. So it's going to be 4/3 pi r cubed. And this is going to be the radius of the core, so I'll label it as such. And when we figure this out, okay, it's going to be 4/3 pi 7 times 10 to the 8th meters divided by 4. All right, so there we go. So the volume that we are going to be working with is this. The power at which we are emitting, all right, is given there. And so what we're looking for is how many fusion reactions are happening per second here. So if we think about this, actually, all we need to find is the energy released per fission reaction. We have that from the previous problem. And what we should do is we should convert this into joules, all right, so that it is easier to do the rest of the conversions here with the watts. So when we do that, we know that there's 1.6 times 10 to the negative 19 joules per electron volt. If you want to go over that conversion again, we have to show it in class. The electron volts, we can cancel out. Remember the mega there, which gives us that 10 to the 6th. So what we end up with here is 4.3 times 10 to the negative 12 joules of energy. All right. So from there, okay, we have our. We want to know the fusions per second, effectively. Okay. So if we have energy per reaction, we'll just call it energy per n. Okay. And we have the energy per time. we can get N per T, all right, if we just do the following, if we take the energy per ton and divide it by the energy per fusion. And so that gives N over T, which is fusions per second, we can call it, all right? So when we do that, let's see here, we have 3.9 times 10 to the 26 joules per second, and let's see, 4.3 times 10 to the 12 joules per fusion. And what we end up with here is an incredibly large number in terms of fusions per second. Okay. So then the question that remains again is the fusions. How many fusions are happening per volume per second, right? So to do that, we have a fusion rate per volume. We have both of those numbers. All right. We plug them in here. What we end up with is about 4 trillion fusions per second per meter cubed. I hope your mind's been blown. And it's an absurd number of fusion reactions we having every second, okay? That's an incredibly large release of energy with that happening. So, because it's such a ridiculous release of energy, all right, we've been trying to do artificial fusion, okay? In other words, trying to confine and control a fusion reaction. There are many issues in doing this, and we will talk about them in class. I want you to read over the packet on your own, all right? But we will talk about these together in class. And yeah, bring questions, you know, do some research. If you Google Operation Castle, you will find some cool videos maybe of thermonuclear detonations in the Pacific in the 50s. When I say that they're cool videos, I mean that they're interesting in the history, not what happened as a result, contamination due to winds that they did not anticipate, and actually some people getting sick and dying from that as well. I think there's some Japanese fishermen actually that ended up dying from it. So check it out, do some research on it. If not, we'll talk about it more in class, and have a good Wednesday or Thursday evening whenever you're watching this.